an asteroid worth $5 billion, an asteroid worth $82 billion, an asteroid worth $10 quintillion. Well, if you look at it that way, asteroids aren't a cosmic threat, but a literal gold mine. Many of you have probably heard that it's now believed that asteroids could contain lots of valuable resources, from water ice to gold and platinum. And that's where we get all these estimates of asteroid values from. Roughly speaking, they take estimates of how much resources could be in an asteroid, calculate their total value based on current market prices. But it would be an understatement to say that these estimates are approximate, and sometimes they may be entirely inaccurate. Moreover, some sources provide entirely different values. The $10 quintillion asteroid Psyche, which I mentioned at the beginning, in Astronaut database has a different value estimate of about $27 billion. Well, anyway, it is true that asteroids do contain various resources and rare metals, and sometimes there should be a lot of them. So it's not surprising that people want to get those resources. These ideas are not new. In fact, Konstantin Tsiolkovsky considered them. Also, this concept frequently appears in science fiction, space-themed games, and so on. But relatively recently, a little over 10 years ago, there was a surge of interest in asteroid mining. Even in Google Trends, you can see two significant peaks in 2012 and 2013. One after another, companies began to emerge with plans to start mining those resources in near future, but then it all sort of quieted down. According to some estimates from a decade ago, by now we should already be developing asteroids, but for some reason it hasn't really started yet. So what's the problem? Well, maybe it's just a dumb idea. Well, let's not be so dramatic. It is quite likely that asteroid mining will eventually begin, but the question is, in what state this industry is right now? So let's talk about what is really there on asteroids, how confident we are about it, how we can mine these resources, what approaches exist, and what the pros and cons are. And also talk about the companies that planned or are planning to start mining soon. And also, will this crash the economy? Because, for example, if rare and expensive metal suddenly becomes abundant, it may no longer be rare and expensive, right? And my name is Andrei, and this is Cosmos Elementary. The Earth's population is growing, technologies are advancing, and there is an increasing demand for various resources. However, it is obvious that these resources are not infinite. For example, the supply of rare metals that are used in production of modern technologies will eventually be depleted. There are estimates based on our current knowledge of the quantity of these resources and rates of consumption that some resources will be depleted in not so distant future, like 40 to 50 years from now. Well, if all of these rare metals are supposed to be abundant in space and they are running out here on Earth, it does seem quite logical to turn our gaze towards space. Clearly, resources are not only found on asteroids, but also, for example, on the Moon and Mars. But today we focus specifically on small bodies. As I mentioned, the idea is not new, but why has it been brought up again recently? Some believe that our technologies have matured enough to begin mining in space. But what exactly is there on asteroids? Most often people talk about something we're familiar with, for example, iron. Or something that immediately associates with something more valuable, like gold or platinum. But of course, these are far from the only types of resources that can be found on asteroids. First of all, water. It exists on asteroids, and also comets, which make up a small portion of near-Earth objects. And some might say, hold on, water? Unlike rare metals, we literally have entire oceans of it here on Earth. But here comes another important point. Resources mined in space don't have to necessarily be transported back to Earth. We can use right where we extract them, in space. And water has a multitude of applications in space. You can create rocket fuel from water. Through the process of electrolysis, you can obtain hydrogen and oxygen from water. Liquid hydrogen can be used as the fuel and oxygen as the oxidizer. Such a combination, for example, is used in Delta IV rockets. Obviously, you need not only to extract water, but also to have specialized equipment in space to actually make fuel. There have been proposals to use water as propellant, heating it up and expelling it in one direction to create thrust. But in the end, it is possible to create fuel depots in space where spacecraft can refuel. One of the main reasons why space launches are so expensive right now is the fact that a significant portion of the rockets and spacecraft's mass consists of fuel. So if the goal is to send a spacecraft to the Moon, Mars, or even outer planets, it won't be necessary to bring all of the required fuel from Earth. Instead, you could just reach a depot, fuel there, and then continue the journey. In theory, this could significantly reduce the cost of space travel and drive the development of space exploration within the solar system. But that's not all what water can be used for. For example, it can serve as a shield against cosmic radiation, which is important for long-duration manned space missions. And of course, water is essential for life support. People need to drink in space, and it also could be used to create oxygen for breathing. Its extraction in space could indeed decrease cost of various types of missions. By the way, for fuel production on asteroids, you can extract not only water, but also methane and methanol. For life support systems, in addition to water and oxygen obtained from it, nitrogen is also essential. There are indeed other areas where resources from asteroids could be useful, such as carbon dioxide, ammonia, and ammonia solution for agriculture, and by the way, they can be also used for growing food in space. For metallurgy on asteroids, there are substances like sulfuric acid, hydrogen sulfide, sulfur trioxide, and other compounds that can be utilized. Next, of course, there are metals such as iron, cobalt, nickel, and gold. Additionally, precious metals from the platinum group are especially noteworthy. Precious metals and metals used in various technologies include platinum, ruthenium, rhodium, palladium, osmium, and iridium. There are also elemental semiconductors like silicon, germanium, selenium, tellurium, and that's not all. In general, there can be an abundance of valuable resources on small bodies in the solar system. These, by the way, could serve as an answer to those who constantly question the importance of space exploration. And if people can be convinced of the importance of fundamental knowledge about the universe, then perhaps the prospect of valuable resources could be more persuasive. Especially considering that many technologies that were initially developed for scientific purposes could be used for resource extraction. Well, we've listed a whole bunch of substances that could be found on asteroids and comets. But the next question is, how do we know all this? That's one of the challenges involved in resource extraction. Before we can start mining resources on a particular asteroid using any method, it's essential to confirm the presence of the desired substances and ensure that they are available in quantities that make such extraction economically viable. But I've already provided examples of specific substances. So how do we know this? There are actually several methods. Of course, not all asteroids are the same, but there are many that are similar to each other, which is why they are categorized in specific classes. Asteroids within the same class share similar physical characteristics and chemical compositions. There are indeed several classifications of asteroids, and discussing the nuances could take a while. However, there are typically three broad categories mentioned, though of course there are others. Firstly, there are C-type asteroids, carbonaceous bodies that have relatively dark surfaces. These are the most common objects, comprising about 75% of all asteroids. They can contain a significant amount of water, typically around 10%, but it can go as high as 22%. They also contain carbon and various organic compounds, as well as volatiles. They are considered the most primitive in the sense that they have undergone the least alteration since the early days of the solar system. Next, there are S-type asteroids. These are siliceous or simply rocky asteroids. They are brighter than C-type asteroids and have undergone some degree of melting. They are composed of various silicates like olivine, pyroxenes, plagioclases, and also contain iron, nickel, magnesium, and small amounts of gold, platinum, and some other metals. And the third type is M-type, also known as X-type. These are metallic asteroids, and they can primarily consist of metals. They may be fragments of larger bodies, such as remnants of their metallic cores. Metallic asteroids can contain 10 times more metals compared to S-type asteroids. They are rich in iron, nickel, cobalt, and have high concentrations of platinum group metals and rare earth elements. Psyche is the most massive known representative of this group. As I mentioned earlier, among near-Earth objects, there is a small percentage of comets, where, in theory, it is possible to mine water and some volatile substances. Certainly, it's a broad classification, but it provides a good enough overview. Now, how can we determine the composition of a specific asteroid?
All existing methods have their limitations and varying degrees of uncertainty. Ideally, of course, obtaining samples of the material from the celestial body of interest is the best way to go, but currently there are very few such examples.
The Stardust spacecraft delivered particles from the comet while to Earth, but the samples were collected from the comet's coma rather than its surface. The Japanese spacecraft Hayabusa did indeed bring back particles from the surface of the asteroid Itokawa. Hayabusa 2 spacecraft retrieved samples from the surface of the asteroid Ryugu, and NASA's Osiris-Rex did successfully deliver samples from the surface of the asteroid Bennu to Earth.
But some might say, wait a minute, if I take a handful of dirt from a random spot here on our planet and bring it to the laboratory, what can that tell us about the composition of the entire planet and presence of valuable resources? However, that would not be a completely accurate analogy.
Earth is a large body that has undergone the process of gravitational differentiation, which resulted in the majority of heavier elements sinking towards the planet's core, while lighter elements remained closer to the surface. This process has given Earth its layered structure, with an iron-nickel core, a mantle, and a crust. Earth is a complex object with rich geological history, tectonic activity, mantle convection, and other intricate processes. But many asteroids have undergone minimal change since their formation, especially when we're talking about small bodies. It's quite likely that their composition is relatively uniform throughout the entire object. Therefore, samples from the surface can tell us a lot about such a body. Of course, it's not entirely straightforward. For instance, a specific area on the surface may differ from the rest of the body, because it was altered by a collision with another type of body. Nonetheless, having samples directly from the body allows us to make some conclusions.
So far, we have only a small amount of material delivered from a few asteroids, but we shouldn't forget about another source of material from asteroids.
Meteorites that we find on Earth are a significant source of material from asteroids. Many of these meteorites could be fragments of asteroids that are still in space. Meteorites have varying composition, and they are classified into different parent bodies or types of bodies based on their characteristics. There are meteorites that have lunar or Martian origins. We determine this by comparing their compositions with samples from the Moon or through chemical composition measurements conducted by rovers on Mars.
Certain types of meteorites are associated with specific groups of asteroids.
For example, it is believed that carbonaceous chondrites are fragments from C-type asteroids, while ordinary chondrites come from S-type asteroids. But it's quite challenging to associate a specific meteorite with a specific asteroid, although there have been such attempts. For instance, it's assumed that meteorites from HED group are fragments of the large asteroid Vesta. The results of laboratory studies on these meteorites on Earth can be compared to measurements taken by the Dawn spacecraft, which visited Vesta. However, in most cases, it's difficult to directly link a meteorite to a specific asteroid. Therefore, we usually learn about the composition of asteroids in general, but not about the specific one. Ideally, samples from a specific asteroid of interest are needed for resource extraction.
If obtaining samples is the best option, the next best approach is to study an asteroid with a spacecraft from close proximity. This could be achieved through flyby missions or even long-term observations from orbit.
Indeed, there is a wider range of choices when it comes to spacecraft missions that studied asteroids up close. Spacecraft have been sent to study not only asteroids but also comets, and even Kuiper Belt objects. Spacecraft typically carry spectrometers, which study the properties of light reflected from the surface of celestial bodies to obtain spectra. This information can provide insights into the composition of the body. Yes, it's focused on the surface, but as I mentioned before, for smaller bodies, it's highly likely that their interiors are similar to their exteriors. And if we combine these measurements with other data such as albedo, size, mass, and therefore density, it allows for an even more precise assessment. So basically, if we obtain data on the surface composition indicating high metal content, and measurements of mass and size suggest high density consistent with the entire asteroid being made of metal, then it's likely that the metal is not only on the surface but extends deeper within the asteroid. And yet, most of our information about asteroids still comes from Earth-based observations. Once again, spectroscopy can help us. Different substances absorb radiation at different wavelengths, and we observe these patterns in the spectrum, as I've mentioned many times before. The challenge with Earth-based observation is, firstly, the asteroids are small and faint objects, making it difficult to obtain high-quality spectra. Spectroscopic measurements are often done in the infrared range. Furthermore, since asteroids are small, in most cases the spectra we obtain are averaged over the entire observable surface. This means that we cannot discern differences in composition between individual regions on the asteroid surface.
The observed spectrum can be influenced by various minerals, and sometimes different combinations of minerals can produce similar spectral signature, making it challenging to interpret which specific combination is present in a given case.
Another useful method is radar observations. When we don't rely on sunlight reflected from the asteroid surface but instead send radio waves ourselves, then receive and analyze the signals reflected from the surface. Spectral studies come in various forms, and they can involve polarization of radiation and models of heat distribution models.
To sum up, we do have methods to gain insights into the composition of asteroids and presence of various valuable resources. When multiple methods are used for a single asteroid, then estimates become more accurate. However, there will always be some assumptions and uncertainties, and also there may be some unknown factors that we don't take into account.
It seems that before we spend millions, if not billions of dollars on asteroid mining, we need something better. After a remote preliminary assessment, on-site reconnaissance is needed. Small bodies in the solar system are primarily concentrated in two regions. The asteroid belt is located between the orbits of Mars and Jupiter, and the Kuiper belt situated beyond Neptune's orbit. Additionally, there are Trojan asteroids. Such as Jupiter's Trojans, it is clear that nobody is going to mine on the Kuiper belt objects, and even not in the main asteroid belt. Mostly they consider near-Earth objects, many of which were likely ejected from the asteroid belt. The word near-Earth can be somewhat misleading, as it may sound like they are always near Earth, which is of course not the case. However, their orbit can approach Earth's orbit, as it is the case with asteroids like Eros, or even intersect it, as it is the case with the orbit of asteroid Itokawa, where the object sometimes ends up even closer to the Sun than Earth. Additionally, at certain moments when both Earth and the object are simultaneously at points in their orbits where they are closest to each other, the distance between Earth and such an asteroid or a comet can indeed be relatively small. Those objects whose orbits come within 7.5 million kilometers or 4.7 million miles or less of Earth's orbit and have a size larger than 140 meters or 460 feet in diameter are referred to as potentially hazardous. Here is an illustration of the orbits of over 1,400 such objects in a single image.
But why asteroids and not Moon or Mars? Each of those options have their own pros and cons.
When compared to Mars, the orbits of near-Earth objects are significantly closer, which translates to fuel savings. These are smaller bodies with much weaker gravity, once again saving on fuel. less energy is required to launch and overcome their gravitational pull. The asteroid Bennu in this image is approximately 500 meters or over 1600 feet in diameter. At the same time, very weak gravity can be a problem, depending on the mining method. Fragments and dust clouds raised during the process can interfere with the operation. In general, weak gravity provides different physical conditions for equipment operation, which can also add complexity to the task. I've already mentioned that large bodies undergo the process of differentiation. On Earth, Mars, and even the Moon, most of those metals are likely deep within the interiors of these bodies. However, bodies smaller than a few kilometers in diameter are not subjected to this process of differentiation, and valuable materials in them are likely distributed more evenly. This is an advantage both for extraction and assessing their composition. Going to Mars for resource extraction is challenging and expensive. By the way, some small asteroids in fact are even proposed to be brought closer, say, to the Moon or even to Earth for resource extraction.
By the way, the entire process of resource extraction could be divided into several stages. First, the identification of the potential target. It is necessary to understand its physical properties and orbital characteristics. Delta V needs to be calculated, which is basically a required change in velocity, or in simple terms, how much energy will maneuvers require. Low delta V is preferable.
Next, understanding how and how fast the asteroid rotates is important. Again, slower rotation makes it easier to work with. Then the size of the asteroid is considered. A larger object potentially contains more valuable resources. Orbital parameters are also crucial, including how close the asteroid gets to Earth and the inclination of its orbit. A high inclination can significantly complicate or even make a mission unfeasible. And of course, determining the type of the asteroid and assessing the content of the resources, first remotely and then sending a spacecraft to the body for on-site reconnaissance. The next stage is extraction or excavation of the regolith and the extraction of ore or minerals from it. Then comes processing and enrichment, separating the desired substance from everything else. And then all of this must be placed in a container for storage for further transport. At each of these stages, there are numerous challenges and also methods to achieve the goal.
There's also an issue of how to anchor to the asteroid for further extraction. There are many options.
Methods for attaching to the asteroids for further extraction vary and include options such as tethering to the asteroid using harpoons, as attempted, though not very successfully, by Philae lander when trying to anchor to Comet 67P Churyumov-Gerasimenko. Hooks, screwing into the object, or even fully submerging into the regolith, and so on. Then there is a question of where to extract resources, on-site, or, as I mentioned, bringing the asteroid closer to the Moon or Earth. This option has been considered, for instance, for smaller objects within 20 meters in diameter. NASA even had a project called Asteroid Redirect Mission, in which a spacecraft was supposed to use special gripers to grab onto a 4-meter asteroid, tow it into orbit around the Moon, where it would be studied and samples would be brought back to Earth. However, the project was cancelled. How to extract resources is an area where both traditional Earth-based methods like drilling, excavation, and blasting are considered, as well as some innovative ideas. Many asteroids are not solid rocks, but what is called a rubble pile. In other words, it's a bunch of separate fragments held together by gravity, but very loosely connected to each other. So you could create an equivalent of a snowplow machine with a rotating part that would launch material from the surface into space, and a robust trap would capture it all. You can extract water, for instance, by heating the asteroid, either partially or entirely, and then capturing the water vapor.
For working with metals, you could use magnets or electrostatic forces, among other methods. Should raw materials and ore be processed on site with equipment on a spacecraft, or delivered to a special processing station in space, or be delivered to Earth in raw form?
But honestly, no matter which methods we discuss at present, it all sounds like a distant prospect at best. Yes, the basic principles are understood, and there is even a selection of the most promising bodies based on their composition and ease of access and operation. However, uncertainties in composition still pose a challenge. Yes, we've even brought back material from asteroids, but of course, that's far from the scale implied by industrial mining. For many of those tasks, there are no ready-to-use off-the-shelf technologies.
Nevertheless, companies that have planned or are planning to engage in this have been already registered. When reading news and popular science articles about asteroid mining from 5-7 years ago, the existence of companies that are planning to engage in asteroid mining are presented as a strong argument for this becoming a reality quite soon. Well, if people have started investing money in it, then it must be possible, right? But let's take a closer look at how things have actually progressed.
In the news I mentioned, there were typically two company names that always appeared: Planetary Resources and Deep Space Industries. They were even mentioned in some scientific papers. The name Planetary Resources emerged in 2012 after a renaming of another pre-existing company. Among the founders of the company were Chris Lewitsky, an engineer who had worked at NASA on projects like Mars, Spirit and Opportunity rovers, and Peter Diamandis, an engineer and the chairman of the well-known X Prize Foundation. The ultimate goal of the company was to mine resources from asteroids, ranging from water to various metals. In the early stages, they wanted to focus on water extraction, and they were developing asteroid exploration systems for this purpose. These systems included infrared spectrometers on small spacecraft that were eventually intended to be sent to asteroids to search for water. The company launched its first mini-satellite into Earth's orbit in 2015 and the second one in 2018.
By 2016, the company had gathered about $50 million in investment, including contributions from famous people like Eric Schmidt of Google and the director James Cameron. Additionally, they received substantial grants. However, it seemed that it was not enough.
In 2018, they failed to secure the expected investments. That led to layoffs, and eventually in 2018 the company, along with its developments, was acquired by a blockchain company called Consensus. Currently, the official Planetary Resources website is not operational. The company that acquired them has created a webpage like this, where it seems to state that they allow the use of Planetary Resources intellectual property by anyone who uses it in good faith. And they've listed the patents that can be read about in more detail. I'll leave a link in the description. The second company, Deep Space Industries, emerged a bit later in 2013. They initially gathered less money, just $3.5 million. They also planned to start with water extraction and turning it into fuel. However, unlike Planetary Resources, who wanted to split water into hydrogen and oxygen to create propellant, they chose a different method: heating and expelling water. This system was their initial focus of development. As far as I know, unlike Planetary Resources, they didn't even launch a single spacecraft into space, and you can probably guess what happened to the company now.
It's gone. More precisely, it was acquired by Bradford Space.
In short, neither of the two most well-known companies ultimately succeeded in achieving their goals. So what went wrong? In an article on MIT Technology Review with a brief history of these companies, two perspectives are presented. Some argue that both companies did a great job of talking about their vision, the bright future and all that, but in reality there was little substance to what they were actually doing.
Others, including founders, blamed the investors. They argued that investors think in terms of 7 to 10 year cycles, at the end of which they expect to start seeing profits. And when, after so many years, they didn't see any profits, they stopped providing funds. They argued that their project had long-term prospects, and they, as creators of the company, envisioned them over decades. Ultimately, their vision didn't align with investors' perspective. Here I have a question. If they had a vision for decades, Why did they initially take investors' money knowing that investors expected some returns within 7 years? Especially considering how underdeveloped or simply non-existent the industry is and how much needed to be done to generate some profits in such a short time frame. Clearly, it was unrealistic.
Another problem with DSI and PR was that they planned to start earning money from space fuel production, but apart from the spacecraft that would extract resources, infrastructure was needed for processing and creating fuel, and this infrastructure didn't exist. And it still doesn't. It's unclear when it will. It reminds me of the story of Mars 1, which I recently covered. Although there were at least some actual launches and more technological developments here, but it seems that their ambitions exceeded capabilities.
But if Mars 1 didn't make it to Mars, does it mean that humans will never set foot on the red planet? I don't think so. Similarly, here, the fact that 2 companies failed doesn't invalidate the entire concept.
After PR and DSI, the fuss around asteroid resource mining died down, although other companies emerged. For example, this is the website of Asteroid Mining Corporation, but there isn't much information about them. Or on the website of TransAstra, there used to be a mention of asteroid resource mining, but now it seems to be gone. In general, right now we are capable of bringing back a few grams of soil for scientific purposes. It requires hundreds of millions of dollars and many years of work. We are still very far from industrial mining on asteroids. We need new technologies at every stage: exploration, mining, processing, storage, and delivery. The question also arises whether we need humans at all for these operations, or if everything can be done solely with robots. We need infrastructure, demand, and the whole venture requires massive financial investments and many years of work.
It is fundamentally possible, but when will it actually happen? It's hard to say. And clearly, one should approach promises of startups that claim that they will do it in a few years with caution. And technology is only one of the issues here. Also, there are economic, bureaucratic, and ethical questions to consider.
Currently, with modern technology, asteroid mining would most likely be unprofitable. If you're mining in space for space, there isn't really a market for it. And here's the chicken and egg problem. Is there no supply because there is no demand, or there is no demand because there is no supply? With the development of technology in future, such mining could become profitable, but when? Furthermore, if private companies are going to be involved in space mining, the issue of ownership becomes unclear. It's not clear how all of this will work.
On the one hand, there is an international space treaty that prohibits claiming ownership over celestial bodies or territories. But on the other hand, the US passed a law that included a provision allowing private companies to appropriate resources from asteroids.
Another question is, if a company were to engage in, let's say, platinum mining in space and start dumping it on the market, how would that affect the global market as a whole? The simple thought that is echoed in many articles on this topic is that if there is suddenly a surplus of rare resources, its price will plummet. Well, here's the problem. If the price collapses because of mining on asteroids, the profitability of mining platinum in space will be in question. And they provide examples like one asteroid containing 175 times more platinum than is produced worldwide in a year. Or maybe on the contrary, the emergence of more rare resources will drive the creation of new technologies and increase the demand for them. Firstly, it's evident that no one will extract all the platinum from such an asteroid at once. Secondly, instead of speculations, it would be great to have more concrete estimates in this regard. And such assessments exist. Kind of. For example, I found a paper with a techno-economic analysis of mining water and platinum on asteroids. Here, calculations are made, models are constructed, but it's important to note that assumptions must be made since we're dealing with prospective technologies rather than existing ones. There are indeed many variables, including the speculative nature of prices for certain resources and the question of demand, depending on which industries utilize materials like platinum. In summary, the authors of this article concluded that the platinum market would not be significantly impacted by asteroid mining, but profitability in general would only be possible under specific and unlikely conditions. These are, of course, just the findings of a single article, and not an absolute truth. Overall, there is indeed limited research on these topics. So, did the companies make overconfident statements about the imminent start of industrial resource mining on asteroids? They did. Are there valuable resources on asteroids? Yes, but we don't know exactly how much. Is it possible and profitable in the near future with current technologies? No. Will it become a reality in future? Possibly. But should we believe those who claim that they will start mining platinum on asteroids tomorrow just because we delivered 5 grams of soil to Earth yesterday? Another question is that in the future such mining may become necessary when resources on Earth are depleted or their extraction on Earth causes greater harm to the environment than mining in space. While there may not be a current demand for resources in space, if someone takes it seriously, invests significant resources, spends years developing the necessary technologies, and resources become available in space, it could indeed serve as a catalyst for further exploration and utilization of the solar system. Only time will tell.
Thanks for watching. Links to all of the sources are as usual down below in the description, and if you enjoyed the video, leave a like, comment and subscribe for more. Bye!